This meeting is being recorded.
All right, great. So welcome to the Ice Giant Systems Seminar Series. And let's see, today we're going to have Dr. Naomi Rowe-Gurney, and I've got a little bio for you here. So let me read that real quick. I just want to say thanks everyone for coming. And this meeting is being recorded, and if it'll be uploaded to YouTube. I'll post it to the website, and it'll kind of go out through the listserv. I'll post sort of a link in the chat to the website where things are usually advertised for future talks. I think next month we might have Dr. Amy Simon, I believe, coming on, and so that'll be a big hit too. So I'll post that in a second. But let me pull up this bio for Dr. Rowe-Gurney, and then we'll get started. Let's see here. So, there it is. Alrighty, so Dr. Naomi Rowe-Gurney received her PhD from the University of Leicester, studying the thermal structure and composition of ice giant atmospheres using archived data from the Spitzer Space Telescope. She's currently a postdoctoral researcher at NASA Goddard Space Flight Center through Howard University, and also serves as an ambassador for solar system science with the James Webb Space Telescope, with a focus on the atmospheres of Uranus and Neptune. She also partakes in significant outreach and public engagement work, now focused mostly on JWST and promoting its use for looking in our solar system. And particularly exciting that I found out while researching you was the fact that you were the first Black woman and the first Black British person to get a PhD from the School of Physics and Astronomy at the University of Leicester. So I just want to say a huge congratulations for that. That's an incredible accomplishment.
Thank you.
Of course. So thank you so much for being here. And I'll let you take it away. And I'll turn my camera off too, just so that I'm not distracting to people, so they're just looking at you. But I'm still here. So go ahead.
Okay, can everyone see my screen and hear me okay?
Yes, it's great.
Okay, great. Okay, so today I'm going to talk to you about my research with Spitzer that started during my PhD at Leicester, and I'm continuing with today in preparation for that JWST data that's coming soon. I'm going to start by giving some background of the data itself from Spitzer. Then I'll go on to talk about the retrievals that we've done using it. And then some of that interesting science and the results that we've got from the retrievals for Neptune specifically, and a little bit about Uranus as well. And I'll summarize with how the JWST will advance our knowledge of both Uranus and Neptune. So my PhD research, when I started back in 2017, was meant to be using data from the JWST just straight away. And because of the delays, obviously, that didn't happen. And so my supervisor, Professor Lee Fletcher at the University of Leicester, he had a contingency plan, thank goodness, and had data from the Spitzer Space Telescope. And Spitzer I'd never really heard of before I started the PhD. It's kind of one of those overlooked spacecraft because it's quite small, but it was launched in the same generation of telescopes as Hubble back in 2003, and it was decommissioned back in January of 2020. It was in an Earth trailing orbit, and as I said, it's pretty small. Its mirror is less than a meter across, and the whole observatory looks at the mid-infrared through to the far infrared. But the data that I have was from the infrared spectrometer, which is in the mid-infrared only from 5 to 37 microns. And that instrument was actually decommissioned in 2011 when it entered its warm phase. So we only had between 2003 and 2011 to get some of this data. So why is the mid-infrared specifically useful for these planets, Uranus and Neptune? So here I have some example images of Uranus from visible through to the microwave, and we can also apply this to Neptune. So these different wavelengths are sensitive to different depths in the atmosphere. So on the right, this shows the vertical structure of a generic ice giant atmosphere, and it shows the stratosphere and the troposphere separated by the tropopause at around 0.1 bar. And we see where each of these wavelength bands senses. So the visible and the near infrared in the blue and the purple, like we observe with the Hubble Space Telescope, for example, senses the cloud tops in the tropopause area and into the troposphere a bit. And then the microwave in green senses deeper into the tropopause. But with the mid-infrared, we can see a lot more. We can sense both the the stratosphere and the upper troposphere. And we call this the middle atmosphere of the ice giant. So it's the stratosphere and the upper troposphere down to around 2 bars of pressure that we can sense with Spitzer. And the images here are Uranus in 2 different mid-infrared bands from VLT Vizier, so ground-based instrument. And that's useful because we can see both the troposphere and the stratosphere, and we can see how both of those regions in the band will show completely different structures of the planet and sense different depths. And so that's also in the stratosphere, it's useful for sensing where a lot of chemical reactions take place. So the stratosphere contains the complex hydrocarbon hazes, so those photochemical hazes that dominate stratospheric chemical processes. So when methane is elevated into the stratosphere, it's broken down into more complex hydrocarbons by photolysis or photodissociation. So you can see methane here at its condensation level around 1 bar. It's elevated by eddy processes and uplift by storms and features, and then when it enters the stratosphere, it's broken down by photodissociation into these complex hydrocarbons like ethane and ethylene, methylacetylene, diacetylene, and others that we'll go into later. So the mid-infrared was a main motivation for using Spitzer to look at the ice giants. So the data comes from the infrared spectrometer, which has 4 separate modules with different wavelength and spectral resolution between 5 and 37 microns. And it has no spatial resolution. So we've got the 0.85 meter mirror, means that we're seeing Uranus and Neptune both as point sources of light. So we're almost treating them like we would an exoplanet or a star, a distant star, and that light is disk averaged. So we actually have multiple epochs of archive data for both planets from 2004 all the way through to 2007. So the Neptune data that we have is from 2004 to 2006. And these near infrared images here from Hubble show how dynamic it was in that time period. And we're focused on the highest quality of data. So the one, the data is usually the latest data with the most average longitudes and therefore the best signal to noise ratio. And that is the Uranus data in 2007 and the Neptune data in 2005. And the Uranus 2007 data was used in previous investigations by Orton et al. 2014, but the Neptune 2005 data was only used for scaling purposes in a recent paper by my colleague Michael Roman, and it's never been modeled before. So we've processed all of the epochs of all of these data sets using a consistent reduction pipeline. And that means that we can directly compare those data sets. So this is the kind of data that we can get. On the left, we have Uranus in 2007. On the right, it's Neptune in 2005. The top panels are in wavelength and brightness temperature units, and the bottom panels are wave number radiance units. And that kind of highlights different areas of the spectrum. So these are global averages of the planet, so multiple longitudes averaged together to create a spectrum that represents the entire planet. And the main constituents we can see are methane, ethane, acetylene. They're all present in both planets. And many of those complex hydrocarbons are also present. And the overall shape of the spectra looks very similar, and that's driven by the hydrogen-helium continuum. hydrogen and helium being their main base constituents. And the differences between these two, we can see the difference in the stratospheric temperatures. So Neptune being further away from the sun, but having a higher temperature in the stratosphere. You can see those hotter temperatures represented in the spectra by giving us more prominent features and also reduced noise, especially you can see at the 10 micron region here where we have ethylene. You can't see much at all at Uranus because these temperatures are so low, and we obviously get too much noise to be able to see what's going on there. So here's a closer look at Neptune. The Neptune spectrum, this is in wavelength and brightness temperature units. And so between 5 and 7 microns in this region, it's hard to model at all for anyone because that's due to the influence of scattered light and maybe also the influence of fluorescence. And so the 5 to 7 micron region, we can't really do in our retrieval models. So most of the modeling that we've done is between 7 and 35 microns. So out at the 7 to 9 micron region, we have the main methane features. And then at 10 microns, we have the ethylene feature that's buried in other tropospheric emission. Again, it's a very low radiance region, so it's very difficult for us to model. And the two prominent stratospheric features come from ethane at 12 microns and acetylene at 13, around 13, 14 microns. And past that, there's a lot of smaller features that we'll go into later. So to model these spectra, we use the optimal estimation retrieval technique, and we use an algorithm called the NEMESIS algorithm, which was developed at Oxford University. So NEMESIS stands for the Non-Linear Optimal Estimator for Multivariate Spectral Analysis. And what this does is it takes in the data that we get from Spitzer, and it creates a forward model using known parameters. And what it does with these two things is it does the retrieval, which iterates over that forward model to get as close to the data as possible without straying too far from the priors that we put into the model, because the priors stop us from getting too unrealistic for our solutions. And those priors come from models and also from previous observations. So the output of NEMESIS are temperature structures, gas composition, vertical structures, clouds, although we treat Uranus, both Uranus and Neptune, as cloudless in the mid-infrared, and yeah, composition. So we use NEMESIS to try and model as much of these spectra as possible to develop a consistent framework for both ice giants. And at Uranus, we used NEMESIS for the 2007 data, and we fit that global average. So the right plots here show the model versus the data for both resolutions. And we've used the results from Orton et al. Investigation as priors. So Orton et al. Did a very comprehensive study of this exact data, and we allowed them to vary because we were modeling the whole range of the spectrum from Spitzer for the first time. They did mostly line by line for different features. And we applied Team V et al.'s disk averaging technique very successfully to the data. And these results are published in Rowe-Gurney et al. 2021. So as I said, Orton et al. Did a global average study, whereas we kind of split up the different longitudes and looked at how those longitudes varied. And you can find more information about that study in that paper. And I mention these results even though this talk is about Neptune, because we use a lot of the same methods at Neptune. So for Neptune, we looked at the global average in 2005, and this Spitzer data have never been modeled before in this way. So that's why we started with Uranus, because we had an idea of what we would find at Uranus because of that comprehensive study that already happened, whereas we don't have those priors to work with from for Neptune. So we've modeled the low resolution from 7.5 to 32 microns, and the high resolution data from 11.4 to 19.4 microns. And most of the same retrieval methods as we developed for Uranus we used here. So like the disk averaging technique, and also the way that we sorted out the line data using correlated K models. And so this contribution function on the right is for both the low resolution at the top and the high resolution data at the bottom. And that shows the depth where different wavelengths are sensitive. And it was constructed using the forward model version of NEMESIS called RadTrans. And these plots are specifically modeled using the MOSIS photochemical model, so the model from Moses et al. 2005. But we had to test multiple different priors for Neptune because we didn't have too much to work with. So we used priors from both those photochemical models and also past observations. And we used past observations from the Akari spacecraft, which is an infrared space satellite that is operated by JAXA, and the TEXES instrument, which is on the IRTF telescope, which is a ground-based telescope. So for the low resolution, we allowed temperature, acetylene, and ethane to vary freely. And the bottom left plot, you can see the fit to the data. And we tested 3 main temperature priors to get to this fit. So the MOSIS, the Akari, and also MOSIS Greathouse, which uses the IRTF TEXES data to kind of constrain a certain region of the temperature profile. And we see these options in the right plot. So the dashed lines are the priors, and the solid lines are the retrieval fits to those priors. And we also did some bracketed retrievals with scalings of plus and minus 5% in the purple and orange. And the MOSIS Greathouse profile is in red. That's an average of the MOSIS photochemical model and the results from those TEXES observations from Greathouse et al. In 2011. And we used this MOSIS Greathouse profile was actually used in an investigation by my colleague Mike Roman in his 2022 paper. And for Neptune. And the retrievals converge where we have good information content and only diverge at those lower pressures. And the MOSIS Greathouse prior gives us the best result with a quasi-isotherm at around 170 Kelvin at those stratospheric levels. So the high resolution results are shown in blue here, and we used the low resolution retrieval as priors because we needed to take advantage of the temperature constraint provided by the methane band that isn't present in the high resolution data. And we had to add forward modeling error to the noisier parts of the high resolution spectrum to get a good fit. And we do see a difference between the temperature retrievals in the same region where the hydrogen quadrupole line is sensitive. So the hydrogen quadrupole S1 line is only in the high resolution data. You can see it in the spectrum there at around 17 microns. And the blue temperature profile here from the high resolution retrieval is fitting better to the original prior, but we found we still weren't fitting the S1 line as well as we wanted. So that hydrogen quadrupole feature is a very useful temperature constraint. And there are a lot of hydrogen quadrupoles very prominent in the Uranus data where it's a little bit cooler, whereas at Neptune we have a lot more interference with them. So the S1 line was really the only one that we could use. Right, so, sorry. Around the same time, we also found we were sensitive to the stratospheric DH ratio. So the DH ratio is derived from the relative abundances of CH4 and CH3D, or methane and monodeuteurated methane. And so we changed the relative abundance profile of the CH3D before rerunning the retrieval. And the figure here on the right shows the chi-squared values obtained from this experiment with different ratios. And so this is the best fit ratio that we found was 5 × 10⁻⁴. That was found to be higher than the ratio from the Akari observations, which we're using as our nominal, and that's in the green band here. So we can see it's 3 × 10⁻⁴ plus or minus 1. That was their results that we were using as a nominal prior to this. And their upper limit is within our 3 sigma errors. But this gives us a hydrogen DH value that's higher than recent papers suggest, but not totally out of the realm of possibility. But again, the fractionation factor that we used is also under debate. So it could be that the fractionation factor is different. And yeah, so what we did with this information, we went back and did the retrievals again with this best fit DH value of 5 × 10⁻⁴. And for the temperature profile, we can see the dashed lines are the ones for the 5 × 10⁻⁴ value. It has a better fit to the prior at lower stratospheric levels, but the quasi-isotherm is hotter at around 175 Kelvin. And we mentioned that we couldn't quite fit the S1 line. So we fit, the fit here is shown by the solid line. And this DH value makes it better, so the dot dash line, but we're still not quite at a level. So this is still ongoing to try and make it an even better fit. And so we also found a much better fit in the methane band as well. So much more within errors for fitting the methane. And so we went back and we made this our best fit, so the 5 × 10⁻⁴ value. So as our results, all of our gas profile priors we used are from the NEMESIS model. So for the low resolution, we retrieved acetylene and ethane full profiles, and the results here on in the bottom left plot. We also did a bracketed retrieval to check the sensitivity to the prior. And we do have a strange increase in acetylene at millibar pressures. And we can't really think of a physical process for this, but it's been a consistent phenomenon throughout testing. So it's looking like it might be real, but I'm not sure. For the high resolution, we also scaled 5 gases. So methyl acetylene needed a large scaling factor to fit. That's in the top right. And below that, you can also see we needed less CO2 than the model. So diacetylene and propane fit the NEMESIS priors, and propene, sorry, fit the NEMESIS priors. And the last gas present is the methyl radical, CH3. And so I wanted to kind of pull this chemical aside and talk a bit more about it, because it's the focus of the paper that I'm writing now. But why is it important, CH3 radical specifically? Well, it's because it is the most important source of ethane. The reaction you can see here, so 2 radicals plus it requires a collision with a third body to stabilize the molecular product, will give us ethane, and ethane is one of the most abundant complex hydrocarbons in the stratosphere. So it gives us a lot of information about these chemical processes that are happening in between the photodissociation of methane and the construction of these complex hydrocarbons. There's stuff going on in between, and it's very useful for photochemical models to understand what's happening in between. And also observations of CH3 are a diagnostic tool to constrain the location of the homopores. Otherwise, it's very difficult to determine using other products due to the complication of eddy diffusion. And so this main double feature is located at 16.5 microns, the main double feature of CH3. And the first detection of methyl at Neptune was by Goddard et al. In 1999 using the SWS on the ISO Infrared Space Observatory. And the right plot here is from their paper showing that 16.5 micron double feature. And Unsuccessfully, it was searched for at Uranus as well by Bergdorf et al. In 2006 in their 2004 Spitzer data, and it was only tentatively observed by Orton et al., but it's not been modeled in this area using the Spitzer data before. So this is Neptune. This region between 15 and 19 microns is our high resolution retrieval. So the red line here is before we added any CH3 into the model. And the black line is the 2005 Spitzer data. So Meadows et al. Identified the CH3 main feature at 16.5 microns. You can see it there. They identified it in the 2004 data, and we can see that very clearly in the 2005 data here. They also highlighted multiple unidentified features that we also see in the 2005 data. And we expected that the addition of multiple species would be needed to fit all of these features. But we thought, okay, we'll start with the main 16.5 micron feature because it's almost definitely CH3 and it's the brightest. So we started with modeling that. So to model CH3, we added it into our retrieval model using the same parameters used at Jupiter by Sinclair et al. In their 2020 paper. And the prior, again, the gas profiles are from the NEMESIS model. And adding this gets us this blue line, which not only covers the main 16.5 micron feature, but also all of the unknown features from the Meadows paper, plus the additional features that we identified at longer wavelengths. So the bottom plot here shows the difference between the forward model with and without CH3. And we noticed that the lines, even though they are showing that these features are definitely there, they're not quite fitting to the features. So we allowed the retrieval to scale to fit a best fit for the whole spectrum. So that's that new blue line. And we find we need roughly twice what the NEMESIS model has to fit the data. So that 1.9 plus or minus 0.3 times the NEMESIS model. And this fits very well. And even with some tweaking that we were doing with the DH ratios and the temperature profiles, we were getting a consistent value of 2 times the NEMESIS model. So with Neptune being a success, we never did this for Uranus when we published that first paper. So we thought, why not attempt to do it with Uranus? Because in the Orton et al. Study, they did see something there, and they thought maybe it's CH3, but they didn't confirm that it's CH3. So yeah, let's use the same data, same method on the Neptune data, the Uranus data. So the SH data doesn't fit as well at Uranus due to our much worse signal to noise ratio because of those lower stratospheric temperatures. And we notice we're still missing some features in the same 15 to 19 micron range, not quite as prominently as the Neptune data. But could this feature here be CH3? It's at the right place. And so we used the same methods again with our NEMESIS model as a prior again, and the small changes are caused by the addition of CH3, so that blue line. And only the 16.5 micron band, it makes a significant difference in that area, and that looks to match the spectrum quite well. So if we zoom in, we can see it does match that feature pretty well. And we're still doing kind of sensitivity testing and error analysis, but it's looking good so far that this is looking like definitely CH3 at that 16.5 micron region. So we've done a preliminary scaling with the best fit that we have at the moment, and we show we need about half of the VMR given in the NEMESIS model, but honestly, I don't trust this data yet. the bad fit of the SH makes it very difficult to tell, and part of future work is to try and get this SH to fit better, maybe by constraining how much of the spectrum we're looking at. Rather than fitting the whole thing, we're trying to fit a very specific range to try and get a better solution. Also, CH3 didn't fit either of these two features shown by the question marks. Neither of these are present at Neptune, so potentially could be something of note. Everything I'm talking about should be in a paper soon, probably with a very lengthy section on how the JWST will or has already been able to resolve more features at high resolution and at better signal to noise ratio. That's especially needed for this Uranus data. So I'm going to talk a bit about JWST and how it will be better, because my job right now is to support solar system scientists who will be using the JWST for planetary system science, specifically in the GTO program. So the GTO program, or Guaranteed Time Observation programs, are awarded to science teams that contributed significantly to the design and management of key hardware and software components of JWST, or helped plan the observatory's scientific mission. And Heidi Hamel is the scientist that was awarded the solar system time, and she is now one of my supervisors, along with Stephanie Milam, who's the JWST Deputy Project Scientist for Planetary Science at Goddard. And both ice giants have this GTO time on JWST, the PI being Lee Fletcher, my old supervisor, PhD supervisor. And there's a fair amount of allocated time, enough to map 360 degrees of both planets. 3 longitudes of Uranus are being observed very soon. The possible window is already open, so we're just waiting for that to happen. And 2 longitudes of Neptune are being observed in June next year. And both will be observed in the mid-infrared and the near-infrared using the MIRI and NIRSpec instruments. So this is the JWST imaging and spectroscopic capabilities across the whole spectral range for all instruments, from 0.6 microns through to the near-infrared, to 28.5 microns in the mid-infrared. And here are the instruments being used for the ice giant GTO, covering the whole wavelength range, but specifically it's their IFUs that we're interested in, or their integrated field units. An IFU generates data cubes, so we get an image where every pixel in that image has an associated spectrum of a very high resolution, and we really want to get these image cubes at all wavelengths that we can for both planets. And this IFU alone is an advancement in a space telescope, and it's also an advancement that the telescope is so big. The comparative size you can see is just it's a crazy upgrade from Spitzer especially. And it's my favorite fact is that the Spitzer mirror is the same size as the secondary mirror on the JWST, which just shows how big the JWST is. And you can see in the right plot the minimum flux detected by various instruments within an acceptable signal to noise ratio. And the 2 Webb instruments there are in blue. And we're more sensitive and have better spectral coverage than Spitzer and also Hubble. And we have better spectral and spatial resolution. So the we not only see these smaller chemical signatures better, we can also see where the disk of the planet each species is contributing to, which is really going to be amazing. And we can see the influence of global circulation, local storm systems, and dark spots. So the MIRI MRS is what we're most interested in, because it's got that similar range to Spitzer between 4.9 and 28.3 microns. And it has a much higher resolving power than Spitzer. Its resolving power is between 1500 to 3500, whereas Spitzer was 100 to 600. So a high resolution spectra that we were getting for Spitzer was only 600. And the lowest that we'll get with JWST is 1500, which is a massive upgrade. And so the left plot here as well shows the field of views for the MIRI medium resolution spectrometer, MRS. It's 4 IFUs that it has. And it almost looks like this instrument was specifically made for the ice giants. This is the field of view that it's going to have for both Uranus and Neptune when it looks at them. And every pixel in these images, remember, will have a spectrum to analyze. So this right plot is a preliminary model of what the MIRI MRS will see when it looks at Uranus, with every spaxel in that bottom image having a spectrum with the resolution in the top one, which is just going to blow all of the science out of the water that we have so far. So with these advancements, these are the main science goals for the Ice Giant GTO program. We're sampling those 3 longitudes of Uranus and 2 longitudes of Neptune over the 360 degrees of the IFU, which will generate spatially resolved global spectroscopic maps that will reveal contrasts in atmospheric temperatures and chemical traces. So we're doing full chemical inventories of species like CH3 due to the much higher spectral resolution and the better signal to noise ratio. We might even find new species. And we're looking at circulation, seasonal or long-term climate changes, weather and storms, and also upper atmosphere that can give us clues to their magnetic fields as well, especially H3+ in the near infrared. And results for Neptune and Uranus will then be intercompared to try to understand the differences between the two. And of course, all of this is going to provide context and motivations for upcoming missions like the Uranus Orbiter Probe, and hopefully one to Neptune as well in the future. So another thing to add is I recently got awarded Hubble time to look at both ice giants around the same time as JWST, so near simultaneous observations. And we're using the WFC3 UVIS instrument to do similar observations to the Hubble OPAL program, or the Outer Planet Atmospheres Legacy program. And it's exciting because we get extra wavelengths into the visible band, completely different to what JWST will be looking at. And also, this is really important because dark spots at both planets are only visible at those blue visible wavelengths. And also with the IFUs or the image cubes, we get a lot of information, but we sacrifice a little bit of spatial detail, and we can get better detail from Hubble in the near infrared to identify those finer features. And the OPAL program has been observing these planets with the Hubble Space Telescope since 2014. So we will also gain temporal context alongside their data set. So there are actually multiple programs looking to observe alongside JWST for Uranus, as well as our program. There's an additional Hubble Space Telescope observation in the UV. There's XMM Newton X-ray observations, and there's also ground-based and amateur astronomy going to happen. And this is seriously going to enhance the science that JWST can do, even with JWST being groundbreaking. Okay, so I will leave you with a summary, and I look forward to your questions. Thank you so much.
Awesome. Thank you so much, Naomi. That was really great. It's great to see that JWST has, plans in the future. In fact, right now, I want to say the window started August 6th, right, which is a few days ago. So
Yeah.
technically, any day now. It's great to see that there's plans, to observe these. And also, you introduced me to a new word. You said spaxel. Is that space
Yes.
pixel?
Spaxel is like a spectral pixel, yeah.
Spectral pixel. Okay,
Yeah.
I love it. That's it's a new word for me. I like it. It's way
Yeah.
easy to say. I love that. Yeah, so right, thank you so much. We can have questions if you'd like to post them in the chat. Feel free to. If you'd like to just kind of go off of mute and ask your question, then that would be great too. I guess I'll start things off with a question, but feel free to type your question out or use the raise hand feature, unmute, or anything like that. So you mentioned this kind of at the end a little bit, and especially with with the decadal survey NASA response. I believe it's next week, sometime maybe next Thursday or something like that. So I know the decadal survey is like fresh in my mind, and so specifically, the Uranus orbiter and probe is sort of on the docket for for potentially being the next flagship. So you mentioned it a little bit, but I was curious, how do you see a mission like that, whether it's Uranus, whether it's Neptune, sort of, helping to supplement your JWST and Hubble observations, or maybe even, using them to fill in some gaps or something, something like that.
Yeah, so it's going to be mostly useful for remote sensing in the fact that we use a lot of photochemical models, and those models need more constraints, especially in things that we can't observe remotely, like helium and the other the gases that don't react, so the noble gases. So yeah, things like that with a probe that you would be able to get, and also with temperature structure as well, like vertical temperature structure, being able to constrain that is something that we really need to be able to do for both ice giants. And when we get with results with Uranus, like we'll be able to apply a lot of them to Neptune as well. But obviously another mission to Neptune would be the best option.
Of course. Okay, great. Any other? Well, let's see. Nick's got a question about CH3D. Yeah, you can if you're able to, you can go off mute and
All right.
Hey, Nick.
Great talk. That's good
Thanks.
stuff. Yeah, I'd one about the differences with that. I always say this wrong. This Akiri or Akari or whatever it's called. So the difference between your results and the previous results for the CH3D. Do you know what's going on there, or have you got any sort of clues as to what might be happening?
Honestly, like the differences, like as I said, the Akari results are like their upper limit is within our 3 sigma boundary. So it could just be that the data is showing something different that is coming up that looks like it's fitting better with CH3D, but it might not be that. It's, obviously with retrievals, it's just the best solution. So I was glad that it fit within the boundaries of the Akari results. But again, like the Spitzer has slightly better range, like spectral range than Akari. So I would say that ours, like being slightly higher, isn't out of the realm of possibility either, and that the outer planets are supposed to have slightly higher DH ratio than the inner ones. So it's not. But then, as I said, the fractionation factor that I used is also under debate. So it could be that the DH ratio is normal and the fractionation factor is different. But again, I'm not a massive expert on those constraints.
Were they using the same wave number sort of ish, or was it like a different wave number that's sensitive to a different pressure or something? I'm just wondering.
A good question. Akari is infrared. I can't remember the exact boundaries that Akari had. It'd be an easy lookup, but I can't remember.
It's what happens when you look at different wavelengths. It's always different.
Yeah.
Yours is always the right one, so it's all good.
Yeah.
All right, cool.
Thanks, Nick.
All right, no problem.
Let's see. Leslie's got her hand raised. Yeah, go ahead. Turn on mute.
That was a great talk. Thanks a lot.
Thank you.
Beautiful results, including the Neptune temperature structure. I've got 2 questions about the temperatures. Do you have a similar? Sorry, I've got 2 cameras, so I don't know which one I'm looking at. Do you have a similar temperature structure in the works for Uranus? And what is the lowest pressures at which you can reliably get temperatures or temperature gradings?
Yeah, so the first question about Uranus, the alternate owl study in 2014, that had an entire paper. So there were 2 papers in that, one focused on the temperature structure and the other one focused on the chemical constituents. So when during my paper, I was looking at that longitudinal variability. So I wasn't as interested in the temperature structure itself, rather the difference in the temperature structure for the different longitudes. So yeah, that study had already been done. And then for the next part, oh yeah, the upper limit. So so we're looking down to around 2 bars, and then the upper limit slightly less easy to constrain. The model itself, we're taking to a certain height, around 10 to the -7 bar, so pretty high up in the stratosphere, but the model isn't as reliable above like 10 to the -6. It starts to, because we don't have the ability to constrain that area as much, not in the mid-infrared anyway. So yeah, again, it's kind of, it's under debate as to how high we can go reliably.
Thank you.
Any other questions? You can put them in the chat, or you can unmute yourself if you'd like. If there aren't any, or if you're currently typing them in. Usually at the end of these, I like to sort of put up a slide of community news, just to sort of make sure that the community is staying up to date on job opportunities, conferences, workshops, things like that. If you need a one-stop shop for ice giant news. So I'm going to go ahead and kind of flash that up right now. So I'm hoping it's this one. So hopefully folks can see that. And so just something that that we like to do to kind of make sure everyone is aware of what's happening in the community. And you can feel free to email me if you want something added to this that can be advertised. And I can also advertise things through the listserv. I think there's 200+ people that are on our listserv. So if you want something that you want 200 people to hear about, then let me know, and I can kind of blast it through our listserv. I know there's links in here, and whenever people put PowerPoints with links on, I'm like, how am I supposed to look at that? So I'm going to copy these into the chat so that everyone can, actually click on the links that I posted and not just staring at them and at a screen. But the main things that I wanted to sort of point out was, like we mentioned earlier, we've got the decadal survey response from NASA that's happening next Thursday, I believe. So that's going to be really exciting, and I'm pretty stoked to hear about that. And then a couple research positions, and then most importantly to me is the Ice Giant System seminar series is going to be having Dr. Amy Simon next month, and so you can register for that through that link. And you can also sign up for the listserv if you haven't already, and you can kind of get reminder emails about registration and kind of other community news. So if there aren't any other questions, then we can kind of close it here and give people an opportunity to go on to their next meetings and refill their water and coffee and that sort of thing. So again, thank you so much, Naomi. That was an excellent talk.
Thank you.
Yeah, and I'm really excited to see those results from JWST. Hopefully,
me too.
Yeah, right. Keep us updated.
Will do. You can keep updated on my Twitter.
Okay.
I put it. The link was on the slides, so hopefully people caught that.
Yes. Yeah, I did see that. Okay. And if you want to put it in the chat too, that might be helpful so people can follow you there.
Sure.
So. Alrighty. Well, yeah, I'll kind of close it here. Thank you all so much for coming. Feel free to reach out to me. My email is on that website. And if you have any questions, or if you'd like to give a talk, that would be great. And of course, share this with your friends, your colleagues. We're always looking to spread the word and kind of get as big of an audience as we possibly can, especially with the decadal coming out. There's lots of new things happening. So thanks so much, everyone. I'll leave the Zoom open for maybe another minute or so in case people want to chat. But yeah, I'll call it here. Thanks, everyone.
Thank you.